instead of having to figure out a numerical representation of our transfer function and then trying to think of different cases of frequency and what the frequency response looks like, we want an easier way to be able to quickly look at a plot or something similar to figure out what the frequency response is, what's happening with both our magnitude and the phase of our transfer function. And so the solution to that problem is something called Bode plots. And so Bode plots are sort of the industry standard of how to convey frequency response information for a circuit. So we're going to get to our Bode plots in a later video, but in order to talk about Bode plots, we need to have a better understanding of decibels and the decibel scale. So before we even look at that, I want to talk about some background on this decibel units. So let's say some background on our units. And the main reason I do this is I know that as a student, it was sometimes confusing to me. Some of you have maybe worked with decibels before. Sometimes you use 10 in the equation, sometimes you use 20. So hopefully this will clarify when we use which one. So our gain in bells is defined as G sub B equals log base 10 of P2 divided by P1. And so P2 in this case is our output power, and P1 is our input power. And so the unit bell is actually named after Alexander Graham Bell, and it turns out that one bell is very large. So one bell, sorry, it should be lowercase b. One bell is large. So typically what we use instead is we'll use decibels. And so of course that's the same sort of metric prefix we've seen with other units. So for instance, we could say 1 bell is then equal to 10 decibels. And so that's the same way if we said 1 volt is equal to 1,000 millivolts. So same basic idea there. So all we need to do then is modify this equation. If we want the same value, we just multiply it by 10. So we say our gain then in decibels, dB, is equal to 10 times our log base 10 of P2 divided by P1. So we just have this 10 out front now. So note, this is if we're dealing with powers. And so oftentimes we'll drop this 10 subscript in our log, and so just assume that if you don't see a subscript, we're talking about log base 10. Okay, so this is the case when we're using the 10 when we're calculating decibels, but sometimes we use 20. So where does that come from? Well, so let's look at sort of a simple network here. So in this network on our input side, we have voltage V1, current I1, and an equivalent resistance looking into our network of R1. On the output side on the right, we have voltage V2, current I2, and a resistance R2. So let's talk about our input and our output power, because after all, that's what that equation for our bells and decibels is relating. So input and output power. So let's call our input power P1 the same as we had on the previous equation. So our P1 is equal to I1 V1. But remember, we also have a couple other forms. If we talk about this equivalent resistance, R1 looking into that network, that's basically saying that we could rewrite that whole network as just a resistor R1. So we could have something like this and have current I1 and voltage V1. So if that's the case, we can rewrite this power as V1 squared divided by R1, or we could also write it as I1 squared times R1. Similar thing for our power P2. We can say it's IV, where we have I2 and V2. We could also say it's V2 squared divided by R2, or we could say it's I2 squared times R2. So we have these various forms of power. So let's say instead of dealing with the powers, we had voltage information, or we wanted to have our equation relate our input and output voltages. Well, let's start with our power expression that we had on the previous sort of page there. We said our gain in decibels is equal to 10 log base 10 of P2 divided by P1. Okay, well, so if we're dealing with voltages, let me substitute into that our expression for our power in terms of the voltages. So we're going to use these two expressions here. So in the numerator for P2, I'm going to have V2 squared over R2. And in the denominator, I'm going to have V1 squared over R1. Okay, so we get something that looks like that. Of course, I can sort of clean that up a little, move our R1 up to the numerator, R2 down to the denominator. So we have 10 log base 10 of V2 squared divided by V1 squared times R1 divided by R2. Well, so both those voltages are squared, so I can pull that squared out, so I can say this is 10 log of V2 divided by V1, so that value squared. And then from log properties, if we have log of A times B, we can say that's a log of A plus B. So let's just add that. So we have log 10 times log base 10 of R1 over R2. So now if we assume that our resistances are equal, that second term is going to go away. So assuming R1 equals R2, we have our second term equals 0. So we get rid of that term. So we have log of 1, which is equal to 0. So what we're left with then is this first part here. And so from another log property, we can take that exponent inside here, this 2, and we can bring it down, and we can multiply by this 10 that's already out front. So we then, our final result is we get that our gain in decibels is equal to 2 times 10, we get our 20, log base 10 of V2 divided by V1. And so if we go through and do a similar thing with the current and we assume that R1 equals R2, we can see that our gain in decibels is equal to 20 log base 10. Again, I'm just assuming log base 10, not writing it explicitly, of I2 divided by I1. So sort of a summary, what we see from that is we're going to use the 10 log if we're dealing with powers, and we're going to use the 20 log if we're dealing with voltage or current. Another important note is that if we're using these two equations here, we want to make sure that we're only using voltage and current magnitudes. So basically we're ignoring any negative signs that might be associated with our currents and voltages. So voltage and current magnitudes. So for instance, if we had our V2 was -5, we would just plug in 5 into this equation here. So now that we have a basis, a better understanding hopefully of our decibels, we're ready to look at our Bode plots.